So welcome to part one of 1,000 parts and rebuilding a duplicate guidance control computer for the Apollo missions. So I saw a video on Vintage Space where Amy described how the Apollo guidance computer worked, and I've been wanting to do some kind of video on explaining to people how general purpose computers work. I decided to look it up to see what kind of CPU it used, and I found that it used nothing but NOR gates. And that was kind of important because I knew exactly what they had done, and then I knew I could rebuild one just because of that. I'll have some theory videos later on to explain how that works. Start off, let's look at a NOR gate. So they're using, NOR gate is typically shown like this. And then you typically have your inputs and outputs. So 0, 0, outputs 1, 0, 1, 0, 0, 1, 1, 0. So here's your input and here's your output. So what a NOR gate actually is, it's a OR gate and then a NOT gate immediately afterwards. So the way the OR gate works, you have your two inputs. 0, 1 is 1, 1, 0 is 1, and 1, 1 is 1. And your NOT gate just does the opposite. So as you see, we just do this, we get a 0, go to the NOT gate, get a 1, just like there. And then all the other three, the inputs all from the OR gate come out 1s, the NOT gate turns it to 0, which are those three. This is a special gate. This is the first IC they made, because with this you can make any other logic gate, and when you do a NOR, a NOT after a normal gate, you just put a little circle on the end instead of drawing it out like you would initially think, something like that. You just put the circle instead. So I've already failed in duplicating it exactly because they used 3 input NOR gates, 2 to a chip, which aren't available anymore, and they probably haven't been available since the 60s. So what I did instead is I ordered these chips. They have 3 input NOR gates on them instead of just 2. And I broke the leg on that one already. So that means I'm going to have 1/3 less chips than they did. And then you can find the top of the chip that has a little spot there. It might be hard to see. So you can paint a little dot to make it easier to see. I always thought they looked like bugs. So you can paint a couple dots for eyeballs or something. Make it a little interesting. Now, this circuit up here is a timing circuit with a 555 chip. They did not have that on there in the Apollo. I have it on there just for testing of the circuit. All it does is make that LED blink. So here's the output wires going from high to low. As a side note, when we talk about 0s and 1s, they go into here. 0 is 0 volts, 1 is 5 volts positive. The Apollo chips, they were resistor transistor technology, which again you can't get anymore, and they were based on 4 volts. These should work anything above 3.5 volts, so 4 volts should work. 5 volts is what they're designed for. I'm going to try and make it run on 4 volts. If it doesn't, I'll just have to switch the power supply to output 5 volts. And they only used a single NOR chip. All it was a 10-pin chip with the 2 3-input NOR gates. In 1959, they ordered 52 from Texas Instruments at $1,000 a piece. In 2019 dollars, that would be $8,800 a piece. They had to use 2,800 of them, so they were paying, if they continued to pay that price, it would be $2.8 million in just the ICs alone. That's not the rest of the computer. Today's dollars, that would have been $24.6 million for just the chips to make it. And just for reference, I bought these chips from an online supplier, 17 cents a piece versus the $1,000 that they paid back then. So things have gotten a little bit better. And then a lot of people talk about transistor count for dies and chips. So each of the Apollo chips, each of the NOR gates has 3 transistors in it. So the Apollo chips had 6 transistors per chip at 2,800 chips. So they had a total of, I think it was, 16,800 transistors to run the CPU. For comparison, the Intel 8088, which was the predecessor to all the modern PCs, the 8086s and so on and so forth, has 29,000 transistors. The 6502 chip, which is from your Atari VCS, your Nintendo, your VIC-20, your Commodore 64, all kinds of things, was 3510 transistors. So as you can see, it's far more complicated and intricate than what your Nintendo had decades later. And that's because they were able to optimize this. We're using only NOR gates for your logic. You can't optimize it, so you end up using significantly more. The more recent i7, for example, by Intel, is 731 million transistors. And then you got the 10 cores, the 6 cores, the 8 cores. You just multiply that by how many cores. And so we're up to in the billions of transistors per chip. Remember, CPU chips are roughly that size. So I have 9 on this. They have 6 billion and something that size. Just for comparison of where we've gone. So this is a normal breadboard, prototyping breadboard. Have ground, have 5 volts. You run on the bus on the top and you run it down each of these strips. I only ran it down these 2 because that's all I'll need. This chip's all powered up. These chips plug right into the breadboard. The Apollo one had flat mount, so they don't have the pins coming down on them like these do for the breadboard. They go out to the side, so they won't work on the breadboard. So when I do the final assembly, it'll have to be different. And you get a data sheet like this. Pin 14 is VCC, which means the 5 volts. Pin 7 is ground, and you can see the 3 gates, what their input pins are, and what their output pins are. And let's draw that chart up again I did for you before, with the inputs and the outputs. So 0, 0 will give me a 1. 1 0 will give me 0, 0 1 will give me 0, and 1 1 will give me 0. Except we got 3, so I don't want to do a bigger chart. So if all 3 inputs are 0 or ground, the output would be positive. So let's wire this one up, see how it works. So we hook the ground pin up. Hook VCC up. Like I said, we'll do a video later on explaining why they use NOR gates and basic gate logic for you. You'd be able to make up a whole circuit yourself pretty easily if you just understand some simple basics. Yeah, so the red's the power, blue's the ground, so this is wired up. Now if you accidentally switch these, which I've done on a NOT chip in college, it gets up to about 200 degrees in about 1.5 seconds. So let's look at the first gate here. I want to set the 3 inputs to ground. Input 1. And I missed. The longer leg is a positive, so we'll take it out of the output of the gate, which is that pin there. Tie a transistor to it, to the ground. And it comes on. I take this off. That pin's actually undefined, but it's probably still grounded, considered zero voltage. So we'll hook the second input to the positive, and it goes out. Pull it out, comes on. And if I do that to any of the input pins, it'll work that way. And that's basically how your NOR gate works. So if you've ever wondered how these little chips that you see everywhere work, you get a diagram like this and they work just like that. And these are logic gate chips. There's all kinds of other chips like CPUs and other crap like that that work different. So let's take that out. Take the power out. So what I have here is a schematic for part of the A1 module, which was the first logic module for the Apollo guidance computer. It has 6 NOR gates, and they're wired up like this. It's part of what they call a scaler. So you have your clock impulse coming in here, which I'm going to emulate with this. And then this changes the timing of the pulse for whatever their needs are. I believe it increases the frequency of the pulse. So the input pulse is like maybe once a second. This will come out twice a second or something like that. And they did that so they could control different components with different speeds. So let's try and wire this up. Let's see if we can get it to work right. We're going to need the second chip because I only got 3 per these chips. There we go. As you can see, it can be challenging to try and debug it with all these little wires. I just ran the wrong wire because I read the wrong thing at the point. So every time this blinks twice, this blinks once. And that's what the scaler does. And it has a whole bunch of more circuits like that to get all kinds of different timing outputs. But right there, we got our first circuit completely working for our Apollo computer. Now, they didn't use breadboards like this, they used multi-layer printed circuit boards. And theirs were 7 layers. One layer was for ground, one layer was for the 4 volts or 5 volts, and then the rest was all this logic wiring. I am unable to find the printed circuit schemes that they had, masks that they had. Not that it would be useful to me because I got 14 output pins or 14 pin chips instead of the 10 pin chips. But it would have been helpful for figuring that out. So I'm going to have to make my own. And the plan is to make it all available to anybody else who wants to try and do it. And I might even see if I can get the boards mass produced and sell the boards online as well. There'll be, I think, 52 of them, because there's 26 logic modules and there's 2 sides to each one. But this is basically how they worked it. You would have an engineer come up, build a logic diagram just like this. Some guy take the pinouts just like this, wire it up on a breadboard, make sure it worked, come up with the printed circuit board designs, which are really simple, and print them out, glue them onto the module, solder the chips in, except they welded them instead of solder them. They covered them in epoxy, and then plug them in one at a time to the computer. Alright, well that's it for this video. Thanks a lot.